Blockchain is a revolutionary technology that's transforming how we establish trust in the digital world. At its core, blockchain is a distributed digital ledger technology that securely records transactions across multiple computers. Unlike traditional databases managed by central authorities, blockchain distributes data across a network of computers. In a traditional system, a single authority controls all the data, creating a single point of failure and control. In contrast, blockchain distributes control among participants, making it more secure and resistant to censorship. Blockchain stores information in blocks that are linked together using cryptography, creating a chain of data. Each block contains essential components: a timestamp showing when the block was created, transaction data recording what happened, and cryptographic hashes that link to the previous block and secure the current block's content. The linked structure of blockchain creates immutability. Once data is recorded in a block and added to the chain, it becomes extremely difficult to alter. If someone attempts to tamper with a block, the cryptographic hash changes, breaking the chain. All subsequent blocks become invalid, making the tampering evident to the network. To summarize, blockchain's key properties include its distributed nature across multiple computers, cryptographic linkage between blocks, transparency that allows anyone to verify transactions, and strong resistance to modification once data is recorded.
The fundamental problem of trust in digital transactions. Before blockchain, digital transactions required trusted third parties, such as banks or payment processors, to verify and secure exchanges. This centralized approach creates several vulnerability points. These intermediaries can become single points of failure, vulnerable to security breaches, human errors, or even malicious actions. Blockchain addresses this fundamental problem by replacing institutional trust with mathematical verification. This allows parties who don't know or trust each other to create a reliable record of exchanges without depending on a central authority. Through this decentralized approach, blockchain technology solves the fundamental problem of trust in digital transactions.
Cryptographic security forms the foundation of trust in blockchain systems. Blockchain's unbreakable trust begins with advanced cryptographic techniques. Public key cryptography allows users to sign transactions with their private keys, creating digital signatures that can be verified using their public keys. Hash functions convert transaction data into fixed-length strings that serve as unique digital fingerprints. Any attempt to alter even a single character in the data would produce a completely different hash, immediately exposing tampering. These cryptographic techniques work together to create an unbreakable foundation of trust in blockchain systems. Consensus mechanisms are the cornerstone of trust in blockchain networks. They solve a fundamental problem: how do distributed systems with no central authority agree on a single version of truth? Without a trusted central authority, participants in a blockchain network must reach agreement through a predefined protocol. The most well-known consensus mechanism is proof of work, used by Bitcoin and many other cryptocurrencies. In proof of work, miners compete to solve complex mathematical puzzles that require significant computational resources. The puzzle involves finding a special value called a nonce, which when combined with the block data, produces a hash that meets specific criteria. The first miner to find a valid solution broadcasts it to the network. This solution allows the miner to add a new block to the blockchain and claim the block reward. Proof of stake is an increasingly popular alternative to proof of work, offering significant energy efficiency benefits. Instead of competing through computational work, validators are selected to create new blocks based on how much cryptocurrency they hold and are willing to stake as collateral. The probability of being chosen to validate the next block is proportional to the size of one's stake. Validators with larger stakes have a higher chance of being selected to create the next block. If validators attempt to approve fraudulent transactions, they risk losing their entire staked amount, creating a strong economic incentive for honest behavior. Both proof of work and proof of stake create economic barriers that make attacks on the network prohibitively expensive. For example, executing a 51% attack on Bitcoin would require billions of dollars in specialized hardware and electricity costs. Similarly, attacking a large proof of stake network like Ethereum would require acquiring and staking billions worth of ETH, which would itself drive up the price, making the attack even more expensive. Furthermore, validators and miners have strong incentives to act honestly, as the value of their hardware investments or staked cryptocurrency depends on the integrity and trust in the network. Let's compare the main consensus mechanisms to understand their strengths and limitations. Proof of work provides excellent security and decentralization, but with high energy costs and limited scalability. Proof of stake dramatically reduces energy consumption and improves scalability, but may offer a different balance of security and decentralization characteristics. Regardless of the specific mechanism, the fundamental goal remains the same: ensuring all participants can agree on transaction validity, thereby establishing trust without a central authority. By making attacks prohibitively expensive and incentivizing honest behavior, consensus mechanisms create the foundation of trust in blockchain networks. Immutability is one of blockchain's most powerful features. Once data is recorded on a blockchain, it becomes virtually impossible to change or delete. This immutability stems from the chain's structure. Each block contains a cryptographic hash of the previous block, creating an unbreakable link. A hash function converts data of any size into a fixed-length string of characters. Even tiny changes to the input create completely different hash outputs. When data in a block changes even slightly, its hash value completely changes. Since each block contains the previous block's hash, any change breaks the chain. To understand why blockchain is immutable, let's see what happens when someone tries to tamper with a transaction in block 1. When data in a block is modified, that block's hash changes completely. This breaks the link to the next block, which still references the original hash. To make the change valid, an attacker must recalculate not just that block's hash, but also update all subsequent blocks in the chain. To successfully alter blockchain history, an attacker would need to control over 51% of the network's computing power. This would allow them to override the consensus and force acceptance of their tampered chain. For large established blockchains like Bitcoin or Ethereum, achieving 51% control is practically impossible due to the massive computing resources required. This immutability is a cornerstone of blockchain technology. It creates a permanent, unalterable record that users can trust without relying on central authorities. Decentralization is a fundamental principle of blockchain technology that distributes trust across a network of computers called nodes. Let's compare traditional centralized systems with blockchain's decentralized approach. In a centralized system, all trust is placed in a single entity that controls all data and operations. This creates a single point of failure that is vulnerable to attacks and requires central authority. In contrast, blockchain's decentralized approach distributes control and data across multiple nodes. This eliminates single points of failure, improves attack resistance, and removes the need for a central authority. In a blockchain network, each node maintains a complete copy of the blockchain, independently verifying all transactions. When a new transaction is created, it's broadcast to all nodes in the network. Each node independently verifies the transaction according to the blockchain's rules. This decentralized structure eliminates single points of failure and makes the system resistant to censorship and attacks. Even if some nodes fail or act maliciously, the network continues to function as long as the majority of nodes remain honest. The remaining honest nodes continue to validate transactions and maintain consensus, creating a robust system where trust is shared among all participants. This decentralization is a key innovation of blockchain technology, creating robust, censorship-resistant networks where trust is distributed rather than concentrated in a central authority. Blockchain networks offer unprecedented transparency while maintaining privacy. All transactions on a blockchain are recorded on a distributed ledger that is visible to all network participants. This creates a verifiable audit trail that cannot be altered, allowing anyone to check the history and integrity of the data. What makes blockchain unique is how it balances transparency with privacy. In traditional systems, data is often private but not verifiable. In blockchain, all transactions are public and verifiable, while sensitive details remain protected. Bitcoin provides an excellent example of this balance. All Bitcoin transactions are completely public and recorded on the blockchain. Anyone can verify that a transaction occurred, the amount transferred, and that it's valid. However, the identities behind wallet addresses remain pseudonymous. This unique combination of transparency and privacy strengthens trust in the blockchain system without requiring trust in any individual participant. Smart contracts extend blockchain's capabilities by automating the execution of agreements without requiring intermediaries. These are self-executing contracts with terms directly written into code. When predefined conditions are met, the contract automatically executes. Smart contracts build upon the blockchain's foundation of trust. They extend the blockchain by adding automated execution capabilities. Traditional processes require multiple intermediaries like lawyers, banks, and notaries. Smart contracts eliminate these middlemen by automating the entire process. The automation of smart contracts reduces human error and bias while significantly improving efficiency in transactions. By automating execution based on predefined conditions, smart contracts further strengthen the chain of trust established by blockchain technology. Blockchain's unbreakable chain of trust enables numerous applications beyond cryptocurrencies. Supply chains use blockchain to track products from origin to consumer. This ensures authenticity and ethical sourcing, replacing paper trails with an immutable digital record. Healthcare organizations implement blockchain to secure patient records while enabling authorized sharing between providers. This gives patients control over their data while maintaining privacy and a complete medical history. Voting systems leverage blockchain to create tamper-proof election records. This ensures votes cannot be altered once cast, while still preserving voter privacy and enabling verification without revealing individual ballot choices. Financial institutions use blockchain for faster, more secure cross-border payments. Traditional transfers that take days and involve multiple intermediaries can be replaced with direct blockchain transactions that settle within minutes at a fraction of the cost. In each real-world application, blockchain replaces traditional trust mechanisms with cryptographic certainty, creating new possibilities for security, transparency, and efficiency. Blockchain technology continues to evolve, addressing several major challenges. Several innovations are emerging to address these challenges and evolve the blockchain ecosystem. Layer 2 solutions, like the Lightning Network, increase transaction speeds by processing transactions off the main blockchain while still maintaining security. New consensus mechanisms like proof of stake and proof of authority dramatically reduce energy usage compared to traditional proof of work, without compromising the trust model. Cross-chain technologies are enabling different blockchain networks to communicate securely with each other, breaking down the silos between isolated ecosystems. As these blockchain innovations mature, we're moving toward a new digital infrastructure where trust is embedded in the technology itself rather than relying on centralized institutions. Blockchain's unbreakable chain of trust will likely become the foundation for a new digital infrastructure, transforming how we establish and maintain trust in our increasingly digital world.